How to Cylon. The Cylon Centurion was an evil class of robot soldier featured in a popular 1970s sci-fi show called Battlestar Galactica. And this is my project about them. So let's get building. I'm using the tried and tested method of construction called the blue tack and spit roast method. Just putting in the discrete components first. Note the correct polarity of the diodes marked clearly on the PCB. Now you notice in the construction I'm continually truing and dressing the components so that they're all in line with each other. Now this isn't just for aesthetic reasons, but this helps to aid in fault finding at a later date if you find the project isn't working properly. So continue to place the components, truing and dressing as we go. When you're happy with that stage of the construction, place a blob of blue tack over the components to stop them from falling out when you turn the PCB over. Now splay the legs out to aid soldering, and notice here how I'm only securing one end of the component at a time. Complete that operation, and when you're happy, turn over the PCB, remove the blue tack, check for true and adjust where necessary, and occasionally address with the soldering iron if you have to. Now turn over and secure the other end of the component using the same technique as before. So I've been experimenting with a non-standard type of soldered joint where I close crop the component lead and then overflow the solder. What I'm aiming for is a domed like finish. So this is the standard soldering technique where the lead goes straight through the PCB, and this is what I'm aiming for. Admittedly not as strong as the conventional method, but it does give a nice aesthetic to the project, and really it's not meant to work in harsh environments or be subjected to strong mechanical forces, and so I think in this instance a valid technique. I use dual sockets for all my IC components. Just check the alignment with that on the PCB. Secure with a bit of blue tack and turn it over and secure diagonally. When you're happy with that, continue with the rest of the soldering as before. With the first pass complete, close crop with the side cutters as before, and then overflow the solder in order to produce that domed effect I was talking about earlier. Now we insert the electrolytic capacitors. The long lead is positive, which lines up with the plus mark on the PCB. Now bear in mind these are physically the same size, but they have different values. This is VR1, the variable resistor. It experiences some mechanical stress in use, so make sure the soldered joints are strong. And this is the power switch, nice tactile feel. There's a right way and a wrong way to put this in, so I've signified that by placing a small dot on the device and the PCB. It's not really a showstopper, it simply means the action will be transposed. Correct operation is in for on and out for off. Now the next part of the project is a little bit tricky. This is the scanning eye module. It comes pre-assembled, it just needs a bit of forming to make it fit onto the PCB. So just take your time there, align the legs, make sure they're splayed out correctly, and it's positive, the long leg, at the top of the PCB. Now just tease the legs in one by one, and after a while they'll all pop in ready for soldering. Now, a word of caution when soldering these LEDs. They are very temperature sensitive, so only solder one leg at a time and don't linger. Now we come to fit the battery holder. The leads need trimming to length, about 1 inch or so, then tinning and solder in position. Once that's been achieved, we can secure the holder using a sticky pad. Place it into position and then press down firmly for a good fit. Also, try and tidy the cables up. Here's one I did earlier. Final part of the assembly is to insert the chips into the DIL sockets. Make note of the cutouts on top of the chips align with the cutout on the DIL sockets. Final inspection, insert the battery and turn on. Nice! Give it a quick wash down and it's good to go.
Please keep away from small children and avoid staring into the medicine scanning eye for extended periods of time. Terms and conditions apply.
This is the circuit diagram for the Cylon project. Here it is in all its glory with its menacing scanning red eye. It's a simple circuit at the heart of which is the 4017 decade counter. Got an arrangement of steering diodes, 6 red LEDs, timing circuit and a power connector. This is a close-up of the circuit's power connector. The circuit's been optimised for 9 volt DC, and that allows me to use the ever-popular PP3 9 volt battery. I like this particular choice of battery because it's small, cheap, compact and readily available. The switch I'm using here is a double pole, double throw latching switch. Now, look closely and you can see I've used both sides of the switch for redundancy purposes, and that feeds into the reverse polarity protection diode. Just in case someone puts the battery in the wrong way round, that will protect the rest of the circuit from coming to harm. This is a decoupling capacitor of 10 microfarads. It's there to mitigate the effects of voltage spikes and other transients on the line, which the 4017 decade counter is particularly sensitive to. Now, this is the timer circuit. It's the ubiquitous 555 timer chip, configured in A-stable mode. These are the timing components, initially set to about 10 Hz. Adjustable by VR1 there. That's the pull down resistor. Gives a nice sharp input to the decade counter. And a point of interest, the pin 5 is not required in this particular circuit, and so for simplicity I've omitted it in this particular application. This is the 4017 decade counter, which, as its name suggests, has 10 outputs, Q0, to Q9, which increment by 1 on every clock pulse received on pin 14. So to the heart of the matter, outputs Q0 through to Q5 sequentially pulse LEDs 6 through to 1 via steering diodes D1 to D6, and outputs Q6 to Q9 sequentially pulse LEDs 2 to 5, and the whole sequence repeats, scanning to and fro, as you can see here. Nice. And the purpose of the steering diodes is to take specific signals from the device and deliver it to the appropriate LED, and to prevent backfeeding of unwanted signals into the device. The brightness of the LEDs is determined by current limiting resistor R1 of 330 ohms. Gives about 8 milliamps of current drawn through each LED, which is a good compromise between illumination and battery power consumption. Points of interest: D1 and D6 are not strictly necessary, but I've included them to ensure an even brightness of the LEDs. Diodes drop about 0.7 of a volt, and if I didn't include them, the LEDs 6 and 1 would be significantly brighter. Pin 12 is not connected in this circuit. It's used to cascade several devices to give more than 10 outputs. Notice the apparent randomness of which the outputs are arranged on this chip. For example, output Q4 is actually positioned on pin 10, whereas output Q5 is actually positioned on pin 1. I don't know the rationale for this, but I assume it's something to do with engineering and manufacturing reasons. But it's something to bear in mind when designing a PCB layout when using this chip. Well, that just about wraps it up for this project. Two very useful chips, the 4017 decade counter and the 555 timer chip. Nice. I hope you enjoyed this project. Please like and subscribe, and I'll be making more projects soon.
By your command.